We're diving into the world of exoplanets today.
Exoplanets, yeah, for anyone who doesn't know, are those planets way out there orbiting other stars. And what we've learned about them this year is, well, mind-blowing is an understatement.
It's completely changed the game, hasn't it?
Absolutely. What's incredible to me is how far we've come. It wasn't that long ago. We weren't even sure exoplanets actually existed, and now...
Now we found thousands.
Thousands.
Thousands. It's like we found the cosmic cookie jar, and it's overflowing.
That's a great way to put it. And they're not just any old planets either. We're talking about crazy diversity here. We've got planets that might have volcanic activity like LP 791-18d.
Volcanoes on other planets. Okay, that's already blowing my mind.
Right. And get this. Others, we're talking about silicate clouds, like on VHS 1256b. Imagine that. Pebbles raining from the sky.
Okay, hold up. Silicate clouds. That's a whole other level of whoa. Okay, before we get ahead of ourselves, let's back up for a second. How do we even find these exoplanets? We're talking about planets trillions and trillions of miles away. It's not like we can just point a telescope and boom, there's an exoplanet selfie, right?
You're right. Seeing them directly is really tough. Most exoplanets are just too small and way too faint for our current telescopes to see.
So how do we do it? How do we find them?
Think of it like cosmic detective work. We've got these really clever tricks to catch them indirectly.
Hit me with it, because I'm dying to know. I do know one way involves waiting for the planet to dim its star's light, kind of like a mini eclipse.
You got it. That's called the transit method. It's actually how we found most exoplanets. Imagine this. Picture a planet passing right in front of its star from our point of view here on Earth, and when that happens, it causes a teeny tiny dip in the star's brightness.
So we're basically seeing the planet's shadow.
Exactly. And the really cool part is, by studying that dip, how long it lasts, how much the light dims, we can figure out the planet's size, how long it takes to orbit its star, and most importantly, how far away it is from that star.
And that distance is super important, right? Because that tells us if that planet is in what's called the habitable zone, that sweet spot where the temperature might be just right for liquid water.
You nailed it. Liquid water, that's kind of a big deal in the whole are we alone department. As far as we know, it's essential for life, at least life as we know it.
So finding a planet in the habitable zone, it's kind of like winning the cosmic lottery.
Pretty much. And one thing that makes this even more complex, the habitable zone, well, it's not the same for every star. It depends on how big the star is and how hot it is. For instance, for smaller, cooler stars, we're talking red dwarfs here, their habitable zones are going to be much closer in compared to our sun, which is a much bigger, hotter star.
So a planet that's super close to a red dwarf might not be a burning inferno. It could actually be pleasant.
Exactly. And the good news is we're finding tons of promising planets around red dwarfs, which is really exciting. Take TOI 700e, it's almost exactly Earth-sized.
No way.
Yep. And get this, it orbits right smack dab in the middle of its star's habitable zone. And the best part, we only discovered it this year.
Okay, so Earth-sized in the habitable zone, that has to be a top contender in the search for life, right?
It's definitely a strong possibility. But here's the thing. TOI 700e isn't our only hope. There's another exoplanet that's been generating a lot of buzz lately, K218b.
Oh, yeah, K218b. And this one's even more interesting because it's not just about size and location anymore, right? We're talking about what's in its atmosphere.
You got it. This is where things get seriously cool. We've got to give a shout out to the James Webb Space Telescope, JWST, for this one.
The JWST, okay, yeah, that's like the ultimate space telescope, right?
Pretty much. And one of the amazing things it can do is it can actually analyze the light passing through an exoplanet's atmosphere. It's like taking a fingerprint of the air itself.
Okay, so what kind of fingerprint did the JWST get from K218b's atmosphere? I'm on the edge of my seat here.
Well, it found methane and it found carbon dioxide, and guess what? We find both of those right here in Earth's atmosphere.
Interesting. So does that mean, is there life on this planet?
Now, hold on. It's not quite as simple as that. We can't jump to conclusions just yet. Finding methane and carbon dioxide on their own, it's not a guarantee of life.
Oh, okay. So what does it mean then?
It's more like, imagine you walk past a bakery and you smell fresh bread. It doesn't automatically mean someone's home baking, but it's definitely a good sign.
I see what you mean. It's a clue.
Exactly. A very exciting clue.
So it's like we're sniffing out clues to life on other planets, just like following the aroma of fresh bread. But K218b, well, it didn't stop at just breadcrumbs, did it?
Right.
There's this whole other molecule they found, dimethyl sulfide, DMS for short.
Yeah.
Now, that doesn't sound like your typical bakery ingredient.
You're right. DMS is a little more, how should I put it, pungent.
Pungent. Yeah, that's a good word for it.
On Earth, it's mostly produced by, get this, marine phytoplankton.
Hold on, phytoplankton, those are like tiny little ocean creatures,
It's
right?
exactly microscopic little guys, but they pack a big smell. They're actually what gives the ocean that distinctive, salty, seaweedy scent.
Wait, so we're talking about the smell of the ocean, but on another planet. That's insane.
Hmm.
So if we're finding DMS on K2-18b, is that saying there could be alien oceans out there?
It's a huge possibility. It's definitely not proof positive. DMS can be created in other ways too, volcanoes, for instance.
Ah, right, volcanoes. We were just talking about those.
Exactly. It could be volcanic activity or even some other process we haven't even thought of yet, but it's definitely intriguing.
Intriguing is an understatement. Okay, so we've got K2-18b with its possible life in the clouds, maybe even alien seas. But let's move on to a totally different solar system. And this one, it's a real humding, TRAPPIST-1. This one sounds like something straight out of Star Wars.
TRAPPIST-1 is, well, it's special. Imagine this, a single star.
Okay, got it. A star, like our sun.
Right, but orbiting the star are, get this, 7, count them, 7 Earth-sized planets.
7. That's like a whole planet party going on over there.
Yeah.
What makes TRAPPIST-1 so important in our search for, ET?
Well, for starters, all 7 of those planets, they're all Earth-sized, which is already amazing. But here's the other thing. The star they orbit, it's a red dwarf, much cooler and way smaller than our sun.
Okay, red dwarf, so that means it's a much smaller, cooler star. Got it.
And all 7 of those planets, they're huddled up real close to that star, closer than Mercury is to our sun.
Wow, really? That's got to make for some cozy planetary orbits. But wouldn't they all be, fried to a crisp being that close to a star?
Not necessarily, and here's why. Remember, red dwarfs, way cooler than our sun, so that means their habitable zones are much closer in too. And get this, 3 of those TRAPPIST-1 planets, we're talking TRAPPIST-1M, F, and G, they orbit right in that sweet spot, the habitable zone.
Wow. 3 potentially habitable planets in one system, the odds of that. But, and maybe this is a dumb question, but with all those planets packed in so tight, wouldn't their gravity mess with each other?
That's a really good question, and yeah, they absolutely affect each other with their gravity.
So it's like a gravitational tug of war all the time.
Kind of, but it's not chaotic, more like a delicate dance. It's actually really stable. And here's the best part. That gravitational dance they do, it helps us study them even more.
Okay, I need details. How does gravity help us study planets trillions of miles away?
Well, as those planets tug on each other, it makes their orbital speeds change little tiny wobbles here and there, and by measuring those wobbles super precisely, using what we call the radial velocity method, we can actually figure out how massive they are.
So we're using their cosmic dance moves to weigh them.
Pretty much. And once we know their mass and we already know their size from the transit method, we can calculate their density, and that tells us what they're made of. Are they rocky worlds like Earth or more like gassy Neptune, that sort of thing?
Wow, it's incredible how much information we can get from these tiny little wobbles. Talk about attention to detail.
It's pretty amazing, right? And speaking of amazing, but also kind of puzzling, we got to talk about one of the most head-scratching discoveries this year, LP 79118 Dex. Remember when we talked about volcanoes on other planets earlier?
Oh, yeah, and I remember thinking, volcanoes? That doesn't sound very life-friendly. It's kind of hard to imagine a relaxing beach vacation with lava spewing everywhere.
I hear ya, but in the grand scheme of things, volcanoes, they can be destructive, sure, but they can also be, well, creative forces too. Remember back in the day, early Earth, volcanoes actually played a key role in forming our atmosphere and our oceans, which paved the way for, well, everything.
So volcanoes, they're not always a bad thing. They can actually help kickstart life in a way.
It's true. They can be a real double-edged sword. And LP 79118 Det, this planet, it's a fascinating case. It's a rocky planet, a little bigger than Earth, and it orbits, you guessed it, a red dwarf.
Of course, a red dwarf. Seems like they're everywhere these days.
They're definitely having their moment in the spotlight. But back to LP 79118 Det, here's the thing. It's right on the edge, and I mean right on the edge of the habitable zone.
Like one step too close, and it's a total meltdown.
Pretty much. It's flirting with being too hot for liquid water, but, and this is a big but, that's where those volcanoes come in.
Okay, I'm listening. How do volcanoes save the day?
Well, scientists think that if, and it's a big if LP 79118D's atmosphere is similar to what early Earth's was like, those volcanic eruptions, they could actually help to stabilize its climate, keep things cool enough for, oceans and lakes, that kind of thing.
Okay, so we're talking about a planet where volcanoes are basically the gardeners, keeping things nice and habitable. The universe is a wild place.
It really is. And speaking of wild, we can't forget about those silicate clouds on VHS 1256b.
Right. Silicate clouds, that's still blowing my mind. Just to recap for us, what makes those clouds so weird?
Imagine clouds made of basically tiny little pieces of rock, dust, basically microscopic sand swirling around up there.
So instead of raindrops, you get like pebble showers.
Exactly. Now, I should say VHS 1256b, it's a gas giant, so not exactly a prime vacation spot, but it does show us the universe is full of surprises when it comes to weather.
That's for sure. It makes you wonder what else is out there. And speaking of which, we got to talk about high-seen worlds. These sound straight out of a sci-fi novel.
So, picture this. An entire planet covered in water, a giant, never-ending ocean.
Okay, now that's my kind of planet. Sign me up. But wait, you mentioned they have hydrogen-rich atmospheres. That doesn't sound breathable, does it?
You're right, not exactly ideal for a midday stroll. Hyson planets, they have these crazy thick atmospheres, mostly hydrogen, and they're pretty hot with really high pressure.
So maybe not the best place to work on my can, and I'm sensing it. But here, you're saying these Hyson worlds, they could still have life on them, even with all that heat and pressure.
Exactly. We've been so focused on finding Earth-like planets, rocky with oceans, but what if it's found a way to thrive in places we never even thought possible? Imagine creatures that have evolved to handle the pressure, the heat, the total darkness of a Hyson ocean. It's mind-blowing.
Mind-blowing is right. It's like the universe is saying, you think you know what life is, think again.
Mm-hmm.
Are there any Hyson planets, on our radar, so to speak?
There is one, TOI 1452b. It's about 100 light years away from us, and it's showing some very promising signs of being our first confirmed Hyson world.
Wow, 100 light years away. It makes you realize how unbelievably big the universe really is.
It really does.
And how much more there is out there waiting to be discovered.
Exactly. And the amazing thing is, we're only just getting started. Every year we have more powerful telescopes, more advanced techniques. Who knows what we'll find next?
It's true. We're living in a golden age of discovery. And I, for one, can't wait to see what we find next.
This has been an incredible deep dive into the world of exoplanets, a universe of possibilities waiting to be explored. This is The Deep Dive, signing off for today. But the search for life beyond Earth, well, it continues.